Welcome back to my YouTube channel Grandpa Mathematics. Today we'll be doing some more problems on exercise 9.2 to see whether the given function is a solution to the given differential equation or not. Then we'll be doing the formation of differential equation whose general solutions are given. Now we have to see y is equal to x sin x is a solution to the differential equation or not. In the difference x y dash is on the left hand side. So differentiate with respect to x, we get dy by dx is equal to x cos x plus sin x into 1. We are using UV form. Du into dv by dx plus v into du by dx. Left hand side of the equation 2 has x y dash. So multiply the equation by x, we get x into y dash. For y dash, we'll substitute the x cos x plus sin x. Then multiply x sin x plus x square cos x. If you see the right hand side of the equation 2, y is there plus x. So we have to see how to get y. So x sin x is nothing but y. So we'll substitute y for x sin x plus x. X is there. So in the x square sin x, x square cos x, you take x outside. Then we get x into x cos x. Now we have to see how to get the value of x cos x in terms of x and y. We know x cos x cos square x is equal to x square into 1 minus sin square x. That is equal to x square minus x square sin square x. Now x sin x is nothing but y. Therefore, this is equal to x square minus y square from 1. Now, from this we get x cos x is equal to square root of x square minus y square. Therefore, 3 becomes left hand side of equation 2 is equal to y plus x into square root of x square minus y square is equal to RHS of equation 2. Therefore, y is the x sin x is a solution to the given differential equation. We have to check whether this function is a solution to the differential equation. Y dash is there on the left hand side. So differentiate this with respect to x, we get x into dy by dx plus y into 1 is equal to 1 by y into, we have to differentiate y with respect to x, so we'll get dy by dx. If we differentiate constant, it will become 0. Now, we'll take y dash to the left hand side. Now we'll take y dash commonly outside. We get x minus 1 by y is equal to minus y. This gives y dash y dash is equal to minus y into y by xy minus 1. So we can rewrite this as y square by 1 minus xy. This is nothing but RHS of equation 2. Therefore, is a solution to the given differential equation. Here, y minus cos y is equal to x is a solution to this differential equation or not. We have to see in the differential equation y dash is there. So we have to differentiate this with respect to x. We get y dash minus, if we differentiate cos y, we'll get minus sin y. Again, we have to differentiate with respect to x. So y dash is equal to 1. We'll take y dash commonly outside. So y dash into 1 plus sin y is equal to 1. Therefore, y dash is equal to 1 by 1 plus sin y. Now take the left hand side of equation 2. X is not there in the right hand side of equation 2. Therefore, we have to replace x plus cos y in terms of y by using equation 1. Y is equal to x plus y. Therefore, we can replace cos y plus x as y. Also, we can replace y dash by 1 plus sin y and simplify, we get RHS of equation 2. Therefore, y minus cos y is equal to x is a solution to the given differential equation. Y dash is then the differential equation, so we have to differentiate with respect to x. We get 1 plus dy by dx is equal to 1 by 1 plus y square into dy by dx. take y dash commonly outside, we get 1 by 1 plus y square minus 1 is equal to 1. Therefore, left hand side of equation 2 is equal to RHS of equation 2. Therefore, x plus y is equal to tan inverse y is a solution to the given differential equation. Differentiate with respect to x, we get dy by dx is equal to, if we differentiate root x, we'll get 1 by 2 root x. So it will be 1 by 2 times square root of a square minus x square. Again, we have to differentiate a square minus x square. We will get 0 minus 2x. Take this equation as 3. Now take the left hand side of equation 2. For dy by dx, substitute the value minus x by square root of a square minus x square. But we know that square root of a square minus x square is nothing but y from equation 1. Therefore, substitute y for square root of a square minus x square. Zero, we'll be getting the RHS of equation 2. Therefore, y is equal to square root of x square a square minus x square is a solution. The number of arbitrary constants in the general solution of the differential equation of fourth order are 4. The number of arbitrary constants, the general solution of differential equation of third order means that will be 3. Number of arbitrary constants of differential equation of second order means 2. The number of arbitrary constants, the general solution of differential equation of first order is 1. Now, the number of arbitrary constants in the particular solution of the differential equation of third order are 0. So, irrespective of the order of the differential equation, the number of arbitrary constants in the particular solution of a differential equation are 0 only. We have to get the equation of family of curves under the given condition. Then we have to say how many arbitrary constants are there. That many times we have to differentiate. And then we have to eliminate the arbitrary constants. Let C denotes the family of curves. Then we have to write the equation of family of curves and see how many arbitrary constants are there. Then that many times we have to differentiate and we have to eliminate the arbitrary constants. Then we will be getting the corresponding differential equation. In each of the following exercises given, we have to form the differential equation representing the given family of curves by eliminating the arbitrary constants a and b. Since the two arbitrary constants are there, we have to differentiate this equation twice and eliminate the arbitrary constants. Differentiate with respect to x, we get 1 by a plus 1 by b into y dash is equal to 0. So we have to differentiate once again. We get 1 by b into d square y by dx square is equal to 0. This gives d square y by dx square is equal to 0. Is the recorded differential equation. In this equation function, there are two arbitrary constants a and b. So we have to differentiate it two times and we have to eliminate the arbitrary constants. Differentiate with respect to x, we get y dash is equal to a into e power 3x. Again 3x is there, we have to get differentiate 3x, again we'll get 3. So it's equal to 3 times a into e power 3x. Here e power minus 2x is there. So if we differentiate e power minus 2x, again we have to differentiate minus 2x, we will get minus 2. So minus 2b e power minus 2x. Now we can eliminate the constant, arbitrary constant b, by multiplying the equation 1 by 2 and adding equation 2. Now take e power 3x to the left hand side so that we'll get only 5a in the right hand side, that is constant. When you differentiate with respect to x, the right hand side becomes 0 and left hand side is in the form of u by v. Left hand side is in the form of u by v. So we know d by dx of u by b is equal to the denominator v square will come, then b into du by dx minus u into dv by dx. In our problem, e power 3x is then the place of v and y dash plus 2y is there in place of u. So v square e power 3x whole square, then e power 3x, then a differential of numerator y double dash plus 2y dash minus, then write this as such, y dash plus 2y, again differentiation of e power 3x. E power 3x into 3 will come. If we differentiate right hand side, 0. Now take e power 3x commonly outside the numerator, we get y double dash plus 2y dash minus 3y dash minus 6y is equal to 0. This gives y double dash minus y dash minus 6y is equal to 0 is the required differential equation of family of curves. So in this equation, there are two arbitrary constants are there, a and b. We have to differentiate twice. Differentiate with respect to x, we get dy by dx is e power 2x ub form. E power 2x into, so d by dx of ub is equal to u into dv by dx plus b into du by dx. So here, can it e power 2x into, then differentiate a plus bx, then we'll get only b. If we differentiate a 0, only b comes, plus a plus bx into differentiation of e power 2x is e power 2x into 2. E power 2x into a plus bx is y. Therefore, for e power 2x into a plus bx, we can replace with the y. Take 2y to the left hand side, we get y dash minus 2y is equal to b into e power 2x. Take e power 2x to the left hand side again, we'll get the constant in the right hand side. Differentiate once again with respect to x, we get this is in the form of u by v. So v square v d v du by dx minus u into dv by dx. We have e power 2x in place of v. So v square e power 2x whole square in v, that is e power 2x, then the differentiation of the numerator y double dash minus 2y dash minus of u, that is y dash minus 2y, then difference from the denominator e power 2x into 2 is equal to 0, because if we different constant 0 will come. Now take e power 2x commonly outside. This for first term, second term. Take e power 2x commonly outside, we get e power 2x into y double dash minus 2y dash minus 2y dash plus 4y is equal to 0. Same problem. We'll differentiate this once again. We get y double dash into 2 times b e power 2x plus 2y dash. Now we'll multiply equation 2 by 2 and then we can subtract. Thereby the arbitrary constant b is getting eliminated. Three minus four gives is the required differential equation. A and b are the arbitrary constants, so we have to differentiate two times and eliminate the a and b. Differentiate with respect to x, we get y dash is equal to uv form e power x into a. If we differentiate cos x, minus sin x will come. So minus a sin x plus b cos x. Again plus a cos x plus b sin x. Now we have to differentiate e power x. We'll get e power x. Now for e power x into a cos x plus b sin x, that can be replaced by y. Again differentiate with respect to x, we get y double dash is equal to e power x into, if we differentiate minus a cos x, if we differentiate cos x, minus sin x will come. So minus b sin x plus minus a sin x plus b cos x If we differentiate e power x only will come. Plus, if we differentiate y dash. So this is nothing but y dash minus y. We call this equation 2. Therefore, this is equal to y dash minus y plus y dash. For e power x into a cos x plus b sin x, we will substitute y. Y double dash is equal to minus y plus y dash minus y plus y dash. So this is the required differential equation. Form the differential equation of the family of circles touching the y-axis at origin. Let C1 be a member of the family of circles touching the y-axis at origin. Let C denotes the family of circles touching the y-axis at origin. The center of the circle C1 is a comma 0. So the equation of a family of circle is x minus a whole square plus y square is equal to a square. We'll expand it and simplify. So x square minus 2xa plus a square plus y square is equal to a square will come. Now differentiate with respect to x, so you get u by b from x square x into 2x plus 2y into dy by dx, 2y into y dash minus x square plus y square into, if we differentiate x, 1 will come, is equal to 0. If we differentiate 2a, that is a constant, so 0. So 2x square, so on simplifying we get 2xy dash plus x square minus y square is equal to 0 is the required differential equation.